Welcome to Empowered Learning. This video will be about how to evaluate the limit of a function by using the squeeze theorem, or sometimes it is called the sandwich theorem. The purpose of this theorem is to give us a way to be able to evaluate limits of a function when the actual function that we're trying to evaluate the limit of is very hard to do from an algebraic standpoint. And so what we do is we say, well, I don't know what the limit of the actual function is that I want to evaluate, but I do know that this function is sandwiched, or its graph lies in between two other functions. And it just so happens that I have information that lets me know that both the function I'm actually trying to find the limit of and two other functions, they both are approaching the same y value as x approaches this particular value that I'm trying to evaluate for the limit. Okay, so if I have that type of information, then I can use the squeeze theorem to basically say that if I want to find the limit of some function, and I'm going to call it g of x as you see it here, we're going to call that the middle function. And I have information about this function so that I know that there are two other functions, f of x and h of x, to where g of x either lies in between or is equal to these functions when x is near this value a that I'm trying to study the behavior of the function at, but doesn't necessarily have to be defined at a. And I know that the limit of the smallest and the largest function both equal to the same real value. Then I know that the middle function, which is the one I'm actually trying to find, has to follow suit. Okay, meaning that the limit of the g of x function as x approaches a will also have to be going to L as well. Now, these graphs that I have here are graphs that I pulled out of the University Calculus textbook. And for the calculus courses that I teach right now, this is the book that I teach out of. So notice here that you have your function f, your function g here, and then you have, h, and then g, and then you have f in the middle. And in this case, what we're saying is that the function g is the smallest one. The one that is f is the one that I'm actually trying to find the limit of. And the one that is h is the largest one. Okay. And so we see how f sort of gets sandwiched in by these two other functions here as x approaches this value c. We also see here that this function u of x is getting sandwiched in by the function 1 plus x squared over 2 and 1 minus x squared divided by 4. Okay, and so for these examples, we use the squeeze theorem for that. Okay, and it's a nice, quick and dirty way for us to be able to figure out what it is that we need to know without necessarily having to know everything. Other such examples here, if you see here, we have sine function, and of course we have y is equal to absolute value of theta, y is equal to absolute value of negative theta. Another example, sine of theta gets sandwiched in by these other two functions here at theta goes to 0. And of course, we see here that our function y is equal to cosine minus 1, it gets sandwiched in by absolute value of theta and by our other function, better known as the x-axis, y equals 0. Okay. So now what we're going to do is we're going to look at some examples on how we would actually apply this squeeze theorem. So we'll start off with a simple example here. And we notice that what we're given is we're given that g of x is a function that lies in between these two functions if I was to graph it. So it lies in between this line and this parabola. For values of x that are greater than or equal to 0. So what we're tasked with finding is what is going to be the behavior of our function g of x. And notice we don't know exactly what g of x is. We just know it's in between these two functions for values x greater than or equal to 0. We want to find out what the behavior of what this unknown function is as x approaches 4 from both the left and the right. So here we've already established one of the two criteria that we need to be able to use the squeeze theorem. Okay, so first thing I had to establish is that my function f of x is less than or equal to g of x, which is less than or equal to h of x, where the g of x function is the one that I'm actually trying to find the limit for. Okay, so now that I know that, there's only one other thing I have to show. Okay, so since we already know that f of x is less than or equal to g of x, which is less than or equal to h of x, then we must show that the limit as x approaches 4 of f of x has to be equal to the limit as x approaches 4 of h of x. And that is going to have to equal the same real number value L. So for us to be able to imply that the limit of this function g of x is going to be equal to something, we have to satisfy both criteria. And again, we've already shown this one because it was given to us. So we just have to make sure that we satisfy the last criteria or criterion. So to do that, we'll say limit of f of x, which is just 4x minus 9. We'll evaluate the limit for that. And because this is a polynomial function of degree 1, meaning that the highest exponent on any variable is a 1, I can use a direct substitution property and just plug this in directly. And I see that this ends up being 7. If I do the same thing for my h of x function, again, polynomial function for any number for that matter is in the domain of a polynomial function. So I can just plug in 4 directly. You'll see here we get 16 minus 16 plus 7, which equals 7. And so we see that the limit of both of these two functions exist as x approaches 4 from both the left and the right. And on top of that, they're both equal to the same thing. And so from here we can say, therefore, limit as x approaches 4 of g of x is also going to be equal to the 7 by way of the squeeze theorem. Okay, and so that is how we use the squeeze theorem to be able to evaluate the limit of a function to where we actually don't know it, but we know enough about it, about its behavior to make an assumption on what it is, or in the instances where it's kind of hard to actually evaluate what the limit of that function would be algebraically. So the next two examples I'm going to do are going to be examples of what I just said. If we look at the function, it's going to be kind of hard to try to evaluate what the limit of that function is algebraically. So we use the squeeze theorem to be able to help us out. Okay, so for this next example, what we're doing here is trying to figure out what the limit of this function is going to be. And in particular, we want to show that the limit of it is going to be equal to 0. Now, what I have here is a graph of this actual function along with the function of square root of x cubed plus x squared, as well as y equals minus x cubed plus x squared. Okay. Now, the reason why I have all three of these functions here, and this shouldn't be this way, so this should be plus like that, and that should be minus down here. So I want to make sure I fix that. So the reason why we have this situation here is because, as you can see, my actual function, square root of x cubed plus x squared times cosine of pi divided by x, is sandwiched in between these two functions here as x approaches 0 from both the left and the right. Okay, so we see that graphically, but we want to know, all right, well, how do I actually do this if I didn't have the graph? Well, if we look here, notice that this is cosine of some angle. And we know that cosine bounces in between -1 and 1. Okay, so that means that the highest value that this function would just be the positive square root of x cubed plus x squared. And the lowest value it would be negative square root of x cubed plus x squared. And so that's where that came from. Okay, and we know that whatever this function is going to have to be in between these two because of what the properties of what cosine acts like as far as its range. Okay, so now that we know that, we have something to work with to be able to figure out, well, what's going to be the behavior of this function as x approaches 0 from both the left and the right. So as I mentioned before, we're going to let our f of x be negative square root of x cubed plus x squared. Positive square root of x cubed plus x squared is h of x. So remember, this is the high function, this is the low function, and g of x is going to be what the actual function that we want to take the limit of. Also, for simplicity, I let theta equal pi divided by x. And so I'm just doing this just to make it look simple. Now, since cosine bounces in between -1 and 1 for all of its values of theta, then if I was to multiply all three sides of this compound inequality here by square root of x cubed plus x squared, I would end up with this situation here. Okay, and so because of that, what we can actually show here is that, one, we can let this be our g of x, this could be our f of x, and this could be our h of x. Okay, and of course we've already said that, but now we see the placement of it, and we know that it is true that f of x is less than or equal to g of x, which is less than or equal to h of x. Okay, so now that we've established that, the only other thing that we need to show here in order to figure out what this limit is by the squeeze theorem is to state that the limit of f of x and the limit of h of x as x approaches 0 has to be equal to the same real number value. Okay, and so that's what we must show. Now, in showing this, notice that this is actually relatively simple to do. From our limit laws, we know that we can take this limit operator here and we can slide it under the radical. We can do the same thing here. And notice that once we evaluate the limit of x cubed plus x squared, this is a polynomial, third degree polynomial. And so we know from our direct substitution property, we can just plug in 0 everywhere where we see x. So we do it here and we do it here. We see that in both instances, we just get 0. So we know from the squeeze theorem that the limit of the actual function that we were trying to find out, which was this one, is going to be 0. And we've actually shown that by using the squeeze theorem. Okay, and so that's how we actually use the squeeze theorem. Okay, Now, to get some more practice with this, let's do this example. And I'm not going to write it out as elaborate as I did before, but here, same kind of thing, right? We know that sine of this is going to bounce in between -1 and 1, okay? So we know this. So because of that, we also know that if I was to multiply square root of x cubed plus x squared, we would have this situation here. Okay. And so from here, we are going to let, and I'm not going to write it, but we're just going to let this be f of x, let this be h of x, and we're going to let this be g of x, okay? So if we let that be that, then of course, our first criterion is that now we know that f of x is less than or equal to g of x, which is less than or equal to h of x, okay? First criterion, check. The second thing that we have to check for is to see that the limit as x approaches 0 for f of x is going to be equal to the limit as x approaches 0 for h of x, okay? And of course, the other thing that we have to put here is that both of these limits, they not only can be equal, but they have to be equal to the same real number, okay? And so what we're trying to do is rule out a case where, well, hey, both of the limits go to infinity, or both of the limits are a does not exist case. And that's not what we mean, okay? So we need to show, or we must show, that this is true. So of course, if we do that, then limit of f of x as x approaches 0 is just going to be minus the situation here. And of course, just like last time, we can take the limit operator, slide it under the radical. And now, because x cubed plus x squared is a polynomial, we can literally just plug in 0 everywhere where we see x. And we see that we end up having 0, okay? If we do the same exact thing for this one, then of course we know we're going to come up with the same outcome. So I'll just kind of skip it and go straight to it, okay? And so because of that, we've shown criterion number 2. And so therefore, we can say that limit as x approaches 0 of all this business here is just equal to 0 via the squeeze theorem. Okay, and that's how we use the squeeze theorem to be able to show that the limit of some function that we either may not know or is very hard for us to try to evaluate directly algebraically. Squeeze theorem's how we actually find a way around that in some instances. So I hope that this video helped to clear up what the squeeze theorem is all about and how to use it. And be looking forward to seeing you in the next video.